Welcome to part 16 of a bunch of videos about parametric curves. My name is Bill Kinney and I'm a math professor at Bethel University in St. Paul, Minnesota. We've been using parametric curves to model motion, physics, and we've been developing calculus tools from an intuitive, physical, geometric perspective to try to understand the curves and the corresponding motion. The main calculus-related thing we've been emphasizing recently is that if you create two functions, first of all a distance traveled function telling you how far you've gone when you move up to a certain time t, and then take what's called the derivative of that function, you get another function called speed of t, the speed function, telling you your instantaneous speed at every moment in time. Geometrically, the value of the speed function gives you the slope of the distance traveled function. In this video we're going to emphasize another calculus concept that's actually related to the first one, though it doesn't seem like it at first, that the area under the speed graph when you start from time 0 gives you the value of the distance traveled function. I'm also assuming that at time 0 you haven't traveled any distance. You're starting at that moment in time. Dist of 0 is 0. So let's go quickly review what we had at the end of the last video. We had this example. We had a function that I've been calling h of t that in this case is a function that increases in value from 0 to 1 as t goes from 0 to 1, but the increase is very slow at first, then it gets greater, and in fact it is maximized at time equals 1/2. Then it goes back to increasing more slowly again. Here is a plot of h of t that illustrates that. Small slope here, large slope here, small slope here. Always increasing though. And when we use that function to model motion, we get the following kind of picture. The motion is in the upper left. Watch it. It starts out slow, then it moves faster, real fast now, then it slows down again. That's the motion. Down here in the lower right, we've got a graph that shows, first of all, the blue graph is the distance traveled. The total distance traveled over the entire interval of time is 5. We go from 0 to 5. And then the red graph is its derivative, the speed function. The value of the speed function, which is given by the height of the dashed line above the horizontal axis, gives you the slope of the blue curve at that moment in time, which is also the same as the slope of this magenta line called the tangent line to the graph at that moment in time. I also happen to notice that in this graph down here, I'd like the labeling to be there, and I realized I could make the labeling be there by getting rid of this labeling command within this plot and instead including it just within the overall show command here in Mathematica. Turns out I also want to make this smaller, couple times smaller, and then I can see the labeling down here like this, and that's good. Alright, so now we want to illustrate the new concept that the area under the speed graph gives you the distance traveled. To do that, I need to make a few more changes here. First thing I want to do is I want in this plot command right here to get rid of the speed function actually and just graph the distance traveled. And that's going to be in blue. So that's the first thing I want to do. The second thing I want to do is I do still want to graph the speed as a function of time, but I'm going to put it in a separate plot. So here I've copied and pasted the plot. I'm going to change dist to speed and change this blue to red. And I'm going to make a couple more changes. First of all, I'm going to add another option in here called filling. And the value I assign to filling is going to be axis. We'll see what that does in a moment. The other change I'm going to make is that I'm going to change this 1 here to a B. What that's going to do is it's going to cause the graph of speed of t to not be graphed completely over the entire animation, but only up to time b. We'd only see the entire graph once b is 1. Alright, I think this is what we want. Let's enter this and then re-enter this. Now watch what happens. If I run the animation, look in the lower right, we see Yes, the red curve is getting traced out as we go, and we also see that the area under the red graph, the speed graph, is being plotted too. Once again, I ask you, what was the main point here? I remind you that the main point of what I'm trying to say is that the area under the speed graph gives you the distance traveled in this situation. The area of this shaded region at time equals 0.5, for example, should be equal to the output of the distance traveled function at that moment in time. It's a little confusing because the scales are different, but this will happen here. What is the area of this shaded region? Well, you can't find it exactly just by eyeballing it, but we could approximate it. If we drew a right triangle by connecting the origin with this point up here and then down over here in this right angle, we would create a triangle whose area could be calculated. Its base would be 0.5, its height would be, well, a little less than 8, close to 8. Multiply 1/2 times base times height, you'd get 1/2 times 0.5 is 0.25, 1/4. The height is about 8, so the area of this triangle that I'm drawing here is about 2. The actual region, though, is a little bit bigger in area, so maybe the true area is about 2.5. What's the value of the distance function at time equals 0.5? It is, in fact, 2.5. Let's try it at another moment in time. Let's try t equals 0.2. All right, now this is closer to looking like an actual triangle, even though it's not exactly. The base would be 0.2, the height would be about, looks like about 4.5. 0.2 times 4.5, base times height, that would be about 0.9. And then 1/2 times that would be about 0.45. What is the distance traveled after 0.2 units? Is it about 0.45? Yes, it's close. It's a little bit more because this is, again, not exactly a triangle. So we have illustrated the concept that the area under the speed graph is the same as the distance traveled in this example. Let's try one more example in this video. Let's go back to our cubic. Alright, so here we go. Run the animation. Look in the lower right. Again, the area under the red graph is going to give you the value of the blue graph. Is that happening? Let's estimate the area under the red graph at 0.2 again. Now this region is almost a trapezoid. You've got this rectangle here whose area is 0.2 times about 5, it looks like. Well, maybe 5.5. 0.2 times 5.5 is 1.1. That would be the area of this rectangle here. What about the area of this thing, which is not exactly a triangle, but very close? Its base is 0.2. Its height looks to be about 15 minus 5.5 would be 9.5. And then, so if I took base times height and then multiplied by 1/2, you can try, you get about 0.95 is the area of that triangle, that approximate triangle. 1.1 plus 0.95 then, which is close to 2, should be the value of the blue graph at time 0.2, and you can see that is about right. Dist of 0.2 is about 2. Let's try one more. Let's try b equals 0.5. What's the area under this graph? It's further from being a triangle, but let's just pretend it's a triangle anyway. Well, if I drew a right triangle like this, with the hypotenuse being like this, that triangle would have an area equal to 1/2 times 1/2 for the base times 15, 3.75. Now this has got an area less than 3.75 by some amount. What's the actual area? It should be dist of 0.5. 2.5 should be the actual area here. I will very quickly close by showing you there's another calculus operation that can confirm this with the speed function. There's a button over here in this Mathematica palette that's a definite integral symbol. If you have calculus, you know about this. If you don't have calculus, you don't know about this. If we put 0 and 0.5 up here and put the speed function here, this operation, this integral operator, turns out to calculate the area under the speed graph. So this should equal 2.5. It's numerically calculating it. So it's taking a little more time, but yes, it does equal 2.5. If I put a 0.2 here, it should equal 1.96, and it does. That's called the definite integral operator, and I'll give you more information about that as we go.